In this video, let's look at a particularly nice kind of spectral sequence called a first quadrant spectral sequence. And this is mostly what we'll deal with in this course. And these are particularly nice because they're concentrated in the first quadrant. So maybe let me define a first quadrant spectral sequence. So a first quadrant spectral sequence just has ERPQ equal to 0 whenever P is less than 0 or Q is less than 0. And so that tells me all the interesting things are concentrated in the first quadrant. And I'm writing this now for a cohomological spectral sequence, but of course we could say the same thing for a homological spectral sequence. And maybe now let me make the remark that a first quadrant spectral sequence, well, one of the things we talked about for a spectral sequence is what it means to converge. And this converges in really a stronger way. And so that's part of why we'll want to deal with these, because they're a little bit nicer. So what do I mean by that? Well, when we talked about convergence in the last video, we saw that really we just wanted that the differential out of each spot was eventually 0. And that even depended on what spot we were looking at. So in a sense, infinitely many things could still be happening. Well, in a first quadrant spectral sequence, when we look at each spot, we look at the bi-degree PQ, then it's still going to depend on what spot we're at. So this is an R0, but maybe it's really an R0 depending on PQ, such that we look at the PQ spot on the rth page, and it's the same as the PQ spot on the infinity page. Well, this should be for all R past R0. So what this says is that you go to each spot, and eventually it's not just that the differentials out are the same, but actually that spot completely stabilizes. And so that's going to be the same as the colimit, and that's what we have on the E infinity page. Okay, so that's a little bit nicer, and we'll draw some pictures of this in a moment. But before we do that, let me say that actually in the best case, sometimes, well, in a better case, sometimes convergence is even better. So we say the spectral sequence collapses at some page, ER0, if there's some R0 such that for all PQ, so now all at once we get some stabilization. So whenever we go past that R0, those spots stay the same. So really this is just saying at some finite stage, the spectral sequence collapses, every spot on the page has stabilized, and so we might as well say that is the E infinity page. Okay, so I said this is, I almost said the best kind of convergence, but what often people do, and most of the spectral sequence arguments that you see in people's research, except the really serious computational spectral sequence folks, is when actually it just collapses at the E2 page. And so the E2 page is the E infinity page, and there's not much computation to be done. But I think it's more interesting when we have some fun differentials. So we'll play around with a lot of things that don't collapse right away, but maybe do collapse at some finite stage. Okay, so let's associate a picture to this because I think that will help make this clear. So say I'm looking at some first quadrant spectral sequence. Okay, what's that going to look like? Well, what I mean by a first quadrant spectral sequence is that I'm 0 everywhere outside the first quadrant. Okay, and then I have a bunch of abelian groups or R modules. Some of these could be zeros. I'm just putting dots to say I don't know what they are. So maybe I have a copy of the integers, a copy of integers mod 2, maybe I have some integers mod 7, and so on. But okay. When I'm drawing this, by the way, I'm drawing P on the horizontal and Q on the vertical. Okay, so when I look at, say, the E1 page, before I do that, let me copy this so I can draw it again for the E2 page really easily. Okay, but when I look at the E1 page, I should have these D1 differentials. Maybe let's remind ourselves how that goes. So dr has by degree r comma minus r plus 1. So our D1 differentials should go over 1, right? They increase p by 1, and they should go down 0. So our D1 differentials look like this. And if you've looked at any books of spectral sequences, you've probably seen these kinds of pictures a lot. So these are all a bunch of D1s, and really they're all different homomorphisms, right? But I'm just by abuse calling them all D1. Notice, by the way, that I didn't draw one over here because this would be a map out of 0, and so it's just the 0 map, and not that you can read that. So there's no need to draw it. Okay, and of course, actually, there continue to be D1 differentials. Okay, now if I look at the E2 page, let's see if I can get this to just appear again. Okay, great. So now I want to look at an E2 page. Now, at each of these spots, I should have taken the kernel of my D1, mod the image of the D1 coming in. I wonder actually if this pointer will work. So I should have taken the kernel of this D1, mod the image of this D1. Okay, and then that's what I put over on the E2 page. So I've taken the homology, so these dots are all new dots, different abelian groups or R modules. And now I consider a bunch of D2 differentials. Well, now these go over 2 and down 1. So from here, I'll have a differential. And here. And here. And now this bottom dot, of course, the differential will be going into 0. And so I usually just don't even draw that. And again, I'm not drawing any differentials coming in on the left because they're all the 0 map. Okay, and continuing on, I've got a bunch more D2 differentials. And so on, maybe forever. So probably I should have put ... A first quadrant spectral sequence doesn't need to be bounded. Okay, so this is just a sampling of these differentials, but here's a bunch of D2 differentials. Now, I want to draw the next page with some D3 differentials, and those should go over 3 and down 2. Yes, arithmetic, okay. But let me do what we often do because there is so much bookkeeping here. Sometimes it's sort of more convenient to just draw these all on the same page. So let me show you what that would look like. Maybe let me try to move that label so I've got a little more space. Okay, so often what we do is just draw all the differentials on the same page. Now, this is misleading because remember, the dots have changed. The actual R modules have changed. We took kernel mod image at each stage. So if you do this, you have to remember a lot. you have to remember that at the D1 differential here, you had some R module. And then when you take the D2 differential out of that spot, it's really mapping out of the kernel of the previous differential, and so on. So here I have my D1, here I have my D2. Often we use a lot of colors to do this, so maybe let me get some new colors. It looks like this spot could support a D3. Of course, it depends what's actually in this place. If it's 0, I might say that it doesn't support any differentials. All of these colors look sort of the same to me. Let's try pink. This one could support a D4. Okay, I kind of went over that dot because my grid is not perfect, but it should skip right over that and land down here on the p-axis. And notice that this spot doesn't support any more differentials, because if I had a D5, it would land below the p-axis where I have a bunch of zeros, and then it would keep getting a longer and longer and longer differential at 0 forevermore. So this is what we mean by a first quadrant spectral sequence stabilizes, because at any given position, eventually your differential will land in 0, in the 0 region, and then it'll be 0 forevermore. So we have some stabilization at each spot. Okay, I said this out loud, but maybe it's worth writing here. So what I'm doing here is drawing all the pages at once. And you have to be really careful when you do that, as I said, because actually the module has changed each time. Okay, so maybe let me just circle that one and say this spot, we say it supports a differential D1 up to D4, but D5 is 0 for degree reasons. And then, of course, forevermore, it's 0. Okay, so these are the kinds of drawings that we'll be doing and trying to do these calculations. And again, as I said, sometimes to sort of ease the notation and to be able to do the calculation quickly, we'll just do all of the pages at once. Okay, let me just finish up with one more sort of aside here, which is that I'm doing this all for cohomological spectral sequences. And part of the reason is that often these come with extra structure. So let me say this sequence of bigraded R modules, our spectral sequence, or I could even say that it's a trigraded R module if you like, that this is really a spectral sequence of algebras sometimes. And it's a spectral sequence of algebras if we look at each page and we see that this is a DGA. So that's a differential graded algebra with respect to this differential dr. And to even be able to say that it's a DGA, then I have to satisfy the Leibniz rule, right? And that Leibniz rule used the degree. So what do I mean by degree here? Well, here we should use the total degree to specify our Leibniz rule. So if I multiply something in the PQ spot by something in another spot, then I'm going to use P plus Q as the degree of that thing when I move the differential past it. Okay, okay, so it's not just that you have an algebra on each page, but it's also that this whole structure respects the algebra structure. So when you go to the R plus first page, you've actually taken the homology of the rth page, and this should preserve that algebra structure. Okay, so often what we'll want to do is use cohomology of spaces, because then we get some algebra structure. And for example, in our Serre spectral sequence, we'll see that if we do a cohomological Serre spectral sequence, then it is in fact a spectral sequence of algebras, and we can really use that to push the calculations forward. Okay, so let me stop there for now, and we'll pick up next time.